So oxidative addition is completed. Second type of reaction, reductive elimination. Reductive elimination. Reductive elimination is just opposite as that of oxidative addition. That is a peculiarity. You know about oxidative addition. Reductive elimination is just opposite as that of oxidative addition. What is oxidative addition? For example, a square planar complex, a coordinatively unsaturated complex, and your metal having very high pi electron density. Metal is electron rich. On reaction with AB, that may be H single bond H, O double bond O, CH3X, RX, ARX, any type of species. What is a reaction? This AB is added here. So M, your product will be an octahedral complex, L, A, B. A and B may be added cis or trans depending on the nature of AB. Okay, so this reaction is called as oxidative addition. What are the peculiarities of oxidative addition? Metal must have very high electron density. Metal must be electron rich. During oxidative addition, coordination number increases by 2 units. Oxidation state increases by 2 units. Here, suppose here oxidation state is +1, then here oxidation state is +3. Oxidation state 2 unit increase. Coordination number 2 unit increase. Metal d electron decreases by 2 unit. Okay, these are some peculiarities of oxidative addition. Then reductive elimination is just opposite as that of oxidative addition. That means, consider a complex, for example, an octahedral complex. Okay, L, A, B. Okay, the peculiarity of A is A and B are anionic ligands. Anionic ligands means they are having negative charge. L is neutral. Neutral ligands does not participate in reductive elimination. Neutral ligands, suppose L, neutral ligands does not participate in reductive elimination. 2A minus, anionic ligand. A and B are two anionic ligand. Heating in presence of a solvent like DMSO. Just opposite reaction. That means this A and B is eliminated. So your product will be AB plus MLL. Okay, this backward reaction is called oxidative addition. Here forward reaction is called as reductive elimination. So your first important thing, oxidative addition and reductive elimination are opposite concept. Okay, so a complex, peculiarity of this complex is this is a saturated complex. Complex must be coordinatively saturated. Complex must be coordinatively saturated. Then only reductive elimination takes place. Coordinatively saturated means, for example, if coordination number is equal to 6, then it is coordinatively saturated. Second point, metal must be electron deficient. That means less pi electron density. Your metal must be electron deficient metal, less pi electron density. Okay, opposite as that of oxidative addition. In oxidative addition, your metal must be electron rich. Okay, L ligands must be neutral and bulky. Your L ligands must be neutral and bulky. When the bulkiness of these spectator ligands, these ligands are called spectator ligands or auxiliary ligands or side ligands, any name, side ligands or spectator ligands or auxiliary ligands. If the bulkiness of this auxiliary ligands increases, what happens? A and B will immediately eliminated. Okay, L ligands must be neutral and bulky. So when complex must be coordinatively saturated, metal must be electron deficient, L ligands must be neutral and bulky, then rate of reductive elimination will be faster. Rate of reductive elimination will be faster. Okay, so these 3 points. Now I think you got an idea what is reductive elimination. 2 anionic ligands are eliminated when you are heating in the presence of a solvent like a DMSO. Okay, then please listen. Consequences of reductive elimination. Consequences. Okay, consequences. First consequence. Here coordination number equal to 6. After reductive elimination, coordination number equal to 4. So coordination number decreases by 2 units. During reductive elimination, coordination number decreases by 2 units. In oxidative addition, coordination number increases by 2 units. In oxidative addition, oxidation state increases by 2 units. Here, oxidation state decreases by 2 units. Okay, in reductive elimination, in reductive elimination, oxidation state decreases by 2 units. Third point, metal d electron changes from dx to dx plus 2. Why? Here oxidation state decreases by 2 units. For example, here oxidation state is equal to 2 plus. Here oxidation state equal to 0. 2 units decreases. Then what about the metal electron? Suppose here metal electron is dx. Then here dx plus 2. Oxidation state 2 unit decreases. 2 more electrons are added. So metal d electron dx plus 2. So remember these informations. During reductive elimination, coordination number decreases by 2 units, oxidation state decreases by 2 units, metal d electron changes from dx to dx plus 2. Then write some examples of reductive elimination, many examples that we have to discuss. So as a part of our introduction, just write 2 examples. Write 2 examples. A metal platinum, here PPS2, here also PPS2, DPPE. What is DPPE? This is DPPE, diphenyl phosphinoethane. Here a methyl group and hydrogen. Heating in the presence of a DMSO type solvent. What is the peculiarity? Here methyl group and hydrogen are anionic ligand. Me minus, charge is -1, hydride H minus. Only anionic ligands will be eliminated. When heating in the presence of a solvent like DMSO, this methyl MEH means methine. Methine is eliminated plus PPH2. Okay, your main product is methane. So that will be your product. Okay, then another example, tungsten. Write another example, tungsten. This is example 1. Example 2, tungsten. Here a CP ligand. Here another CP ligand. Methyl. Heating in the presence of a solvent like DMSO. What happens? Methyl and methyl are anionic ligands. So these two will be eliminated so that your product will be Me. Ethane will be your product plus the remaining portion of the complex. So this type of reaction is called as reductive elimination. Thermodynamics of reductive elimination. Thermodynamics of reductive elimination. You know the basic thermodynamic equation, delta G equal to delta H minus T delta S. For a reaction to be spontaneous, your delta G must be negative. Delta G must be negative for a reaction to be spontaneous. Delta G is negative when two conditions. First one, if your delta S is large positive, or delta H is large negative. When the entropy change is large positive or enthalpy change is large negative, then delta G is positive. So in your reductive elimination, you know, for example, an octahedral complex L, A, B, A and B are two anionic ligands. You are heating in the presence of a DMSO type solvents. What happens? This A and B is eliminated. So you will get the AB as your main product plus a square planar complex. Okay. So please listen. Here number of reactant molecule equal to 1. Only one reactant molecule is there. Number of product molecule equal to 1 plus 1, 2 molecules is there. So as a result of reductive elimination, the number of molecules increases. When number of molecules increases, you know, disorder increases. When disorder increases, entropy increases. Entropy increases means delta S will be large positive. If delta S is positive, then that reaction will be thermodynamically feasible. Clear? Once again, here in reductive elimination, your number of reactant molecule is 1 and number of product molecule is 2. As a result of reductive elimination, number of molecules increases. When number of molecules increases, disorder increases. Disorder is actually called as entropy. So your entropy of the system increases. When entropy increases means it becomes large positive. Large positive means your reaction is thermodynamically favorable or feasible, or you can say that reductive elimination reaction is an entropy driven reaction. But oxidative addition reaction is an enthalpy driven reaction, but reductive elimination is an entropy driven reaction. This type of statement type of questions are favorite in latest CSIR net exam. Okay, mostly this type of statements are asked, whether it is entropy driven reaction or enthalpy driven reaction. Oxidative addition is enthalpy driven, whereas reductive elimination is entropy driven reaction. Clear? So moving to the mechanism of oxidative reductive elimination. Mechanism. First mechanism, three mechanisms are there. First mechanism, concerted mechanism. First mechanism is concerted mechanism. Concerted mechanism is followed when A and B are cis to each other. When A and B are cis to each other. Okay, A and B are the two anionic ligands. So your first mechanism is concerted mechanism, and that is followed when you are eliminating anionic ligands. A and B are cis to each other. For example, metal, let it be an octahedral complex. Here an L is there, L, here an A and B. Heating in the presence of a DMSO type solvent. DMSO type solvent. Here L is a neutral bulky ligand. A and B are anionic ligands. And your anionic ligands are cis. That means they are at an angle of 90 degrees. So they are cis to each other. Okay. And one of the conditions for reductive elimination is your eliminating group must be cis to each other. Eliminating group must be cis to each other. That is the favorable condition. A and B, that anionic ligands must be cis to each other. So in that case, the mechanism followed is concerted mechanism. But when you are reading standard textbook, those groups which are trans to each other also undergo elimination. Those groups which are trans to each other also undergo elimination, but their mechanism is not a concerted mechanism. Their SN2 mechanism and radical mechanism are favored. That I will explain in the next section. Okay. So here, primary condition for elimination is what you are eliminating, that must be cis to each other. So in that case, which mechanism is followed? Concerted mechanism is followed. So in the first case, a transition state will be formed. A transition state, please listen, transition state, the bond between metal and A starts to break, the bond between metal and B starts to break, a new bond between A and B starts to form. Okay, so this bond is a breaking bond, this is a breaking bond, this is a forming bond, and this is a transition state. So bond breaking and bond making, or breaking of bond and formation of bond taking place in a single step, such a reaction is called concerted reaction. Bond breaking and making in a single step. Okay, so immediately it will be converted into AB. A and B forms a bond plus your square planar ML4. Square planar ML4. So this type of mechanism is called concerted mechanism. Only follows when these two A and B are cis to each other. Then only this formation is possible. Bond formation is possible. Okay, so concerted mechanism followed when A and B are cis to each other. Clear? So that is an important point. Then second mechanism. Second mechanism. Second mechanism is stepwise mechanism. Stepwise mechanism or SN2 mechanism. Stepwise mechanism, or it is also SN2. This is followed when A and B are trans to each other. What you are eliminating, they are trans to each other. Normally when they are trans to each other, reductive elimination does not take place, or the rate of reductive elimination will be very slow compared to cis. Compared to cis, always trans rate of elimination is slow, but trans elimination is also possible by another pathway called stepwise mechanism or the SN2 mechanism. For example, consider M, L. Your anionic ligands A and B are trans to each other. More accurately, this A and B can be, your A is a methyl group and B is a halide X. In the first step, you are heating in the presence of a solvent like a DMSO. What happens is this X minus group will be eliminated. In the first step, the trans X minus group will be eliminated. So minus X minus, so that you will get metal, ligand, 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 ligand. Here a CH3 group is there and metal having positive charge. Then in the next step, your eliminated X minus will attack from the back side of methyl group. That attack is an SN2 attack. Okay, in the first step, your halide ligand is eliminated. Then a coordination number 5, a square pyramidal intermediate will be formed. Then X minus will attack the CH3 from the back side. So CH3X is eliminated. CH3X as the product plus M, L, L, L. Okay. So this will be your product. ML4 plus CH3X. Okay. So SN2 or this stepwise mechanism is favored when they are trans to each other, but rate of elimination when they are trans to each other is very slow compared to cis to each other. Mostly cis is favored. Okay, clear. So this is called stepwise mechanism. First step, your halide is eliminated. That will attack from the methyl group from the backside attack. So CH3X will be eliminated. Then one extreme case of SN2 is radical mechanism. One extreme case of this stepwise mechanism is radical. So one more mechanism is also there, that is radical mechanism. Please listen. Third one, radical mechanism. If sterically crowded tertiary alkyl groups are present. If sterically crowded tertiary alkyl groups are present, radical mechanism is favored. Radical mechanism is favored. Sterically crowded tertiary alkyl groups are present, radical mechanism is favored. For example, PT, this is phenanthrene ligand. Phenanthrene ligand, and here carbon with 3 methyl group, and here an X ligand is there, heating in the presence of DMSO. What will be the product? Your anionic ligands are trans to each other, so rate of elimination is very slow. But in the first step, your X minus will be eliminated. Then that X minus will attack on the backside, but the backside is sterically crowded backside. 3 bulky methyl groups are present. Clear? Here the eliminating anionic ligands are trans to each other, so concerted mechanism is not possible. But here which mechanism is possible? Stepwise mechanism. In stepwise mechanism, first step your halide is eliminated. In second step, this halide attack the backside of this carbon, but backside is sterically crowded backside. So SN2 is not possible. Instead of radical mechanism is favored. That means both these bond undergo homolytic cleavage. And a radical pathway is formed, so that your final product will be tertiary butyl halide. That will be your final product. CH3 thrice CX. Okay, so 3 mechanism, most in 99% case concerted mechanism is followed. So these are the mechanisms of productive elimination reaction. Okay, then when more than one alkyl groups are present, when more than one alkyl groups are present, what will be the product? More than one alkyl group. For example, metal, okay, an octahedral complex. Here ligand, here CH2, CH3, not more than one alkyl group, more than one anionic groups, more than one anionic groups. CH2, CH3, here CH3, here hydrogen. Heating in the presence of DMSO. What will be the product? Here more than one anionic groups is present. It's an octahedral complex. This is the base, square planar, axial, two axial. Okay. So what are the axial ligands? So anionic ligands present here. CH3, CH2, alkyl group minus charge, methyl minus, hydride minus. You know, anionic ligands are normally eliminated in reductive elimination. Anionic ligands are eliminated. But here three anionic ligands are there. All are cis to each other. Why all are cis to each other? These two are cis to each other because they are in the adjacent position of the square plane. And this CH2, CH3 is in the axial position. You know the axial ligand is cis to all the base square plane ligands. Clear? For example, this is the square, one axial below. This axial ligand is cis to all the base four square plane ligands. So definitely all the three ligands are cis to each other. My question, which will be your major product or which one will be eliminated? What are the possible products? What are the possible products of reductive elimination? First one, CH3 and hydrogen can be eliminated. So that first product CH3H. Second possible product, this CH3 and CH2 CH3 can be eliminated. So that second product is CH3 CH2 CH3. Clear? First one these two eliminated, second one these two eliminated, third one these two eliminated, this and this hydrogen. So third possibility CH3 CH2 H. So possibility of three products. My question, which one will be your major product? Which one will be your major product? Okay. So order of elimination. Write a note. This is your hint. Order of elimination. Order of, when more than one anionic ligands are present, order of elimination is CH. Most probably CH greater than, HH elimination greater than, CC elimination greater than, CX elimination greater than, CX elimination greater than, where X equal to nitrogen, oxygen or halogen. Nitrogen, oxygen or halogen. So this is the order of elimination. Okay, very important. This data is given in standard textbook. Okay, so more than one eliminations are possible. First priority, elimination of a carbon and hydrogen. Elimination of carbon hydrogen bond, elimination of HH, then elimination of CC, then early elimination of CX. In this case, a carbon hydrogen CH elimination. Here in the next case, CC elimination, carbon carbon CC elimination. Here also CH elimination. Clear? Clear. In this case, the new bond formed between carbon and hydrogen. New bond formed between carbon and hydrogen. Here new bond formed between carbon and carbon. Here new bond formed between carbon and hydrogen. Is it, which elimination is most favorable? CH elimination, then HH, then CC, then CX. X may be nitrogen or oxygen or halogen. So definitely CH elimination will be greater. So 1 or 3. Second is cancelled. Second is cancelled because that is a CC elimination. So CH elimination is favored. Then among 1 and 3, which will be your major product? Then second hint, most electron rich alkyl group. Most electron rich alkyl group have a high rate of elimination. Most electron rich alkyl group. Most electron rich alkyl group have a high rate of elimination. So these are the two hints. Okay, first one, whenever Cc and CH is there, definitely CH elimination is favored. Here this is also methyl hydrogen, ethyl hydrogen. Among these, which one will be your major product? Most electron rich alkyl group have higher rate of elimination. Here this is methyl group, this is ethyl group. You know, due to the plus I effect of this group, inductive effect, this is an electron rich group. When number of carbon atom increases, plus I effect increases, and that is an electron rich group. Comparing methyl group, your ethyl group is more electron rich. Comparing methyl group is more electron rich. So definitely ethyl elimination is favored. That means CH3 CH2H will be your major product. So very important. Okay, so CH3 CH2H. So this is the order of elimination. Please note this point: CHHH CCCX. When two alkyl groups are there, more electron rich alkyl group have a high rate of elimination. Okay, then please write a question. Write a question. When more than one anionic ligands are present, second question, RH, rhodium, here hydrogen, here CH2, CH3, here PPH3, PPH3, here also PPH3, here PPH3, and here CH3. Heating in the presence of DMSO like solvents. PPH3 is neutral, PPH3 is neutral, PPH3 is neutral, but alkyl group anionic, alkyl group anionic hydrogen. Dear students, which one will be eliminated? Okay, 1 second. 1 second. Yes, same question. Which one will be eliminated? A rhodium based. Which one will be CC elimination or CH elimination? Which is favored? CH elimination is favored. Among the CH, which one? Among the CH, which one most electron rich? Comparing methyl and ethyl, ethyl is most electron rich than hydrogen. So these two will be eliminated. So your product will be ethane. Ethane will be your product. CH3 CH2H or CH3 CH3. Ethane will be your product. Okay, then third question. RH, here hydrogen, here NH2, here a CH3, and here PPH3, 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 heating in the presence of a DMSO like solvents. Sometimes simply heating will be given. Okay. So what will be your product? NH2 minus anionic, hydrogen minus, CH3 minus. What is the order of elimination? CH, CC, CH, HH, CC, then only CX. X is here nitrogen is a heteroatom. Heteroatom elimination having least probability. So definitely CH3 and H will be eliminated. So your product will be methane. Methane, CH4 will be your product. Clear? Next question. Right, fourth question. Fourth question. Rhodium, H, sorry, CH3, CH2, CHO, and CH3 thrice. Heating in the presence of a DMSO like solvents. Like solvent. Which one will be eliminated? carbon, carbon, carbon. There is no hydrogen. So CH, HH, CC. So all are CC elimination. All are CC elimination. Then among these, most electron rich will be eliminated. You know, aldehyde group having electron withdrawing nature. Aldehyde group is electron withdrawing. Carbonyl group is electron withdrawing. So definitely these two will be eliminated. Carbonyl group having electron withdrawing nature. So it is not an electron rich group, rich carbon. This sp3 carbon is not an electron rich carbon. You have to account the electron richness of that carbon. That is not an electron rich carbon, deficient. So your product will be CH3 thrice C CH3. Okay, so that will be your product. That's called neopentane. Neopentane will be your product. Clear? Then write the next question. Next one, rhodium. Here PPH3, 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 hydrogen, hydrogen, OCH3. Heating in the presence of a DMSO like solvent. What will be your product? OCH3 is heteroatom, least favored. So these two hydrogens are eliminated. So your product will be H2. H2 will be your product. Clear? Okay, next one. Next one, PT, PPH3 twice, PT, PPH3 twice, methyl, methyl, okay, with an alkyne, pH, see triple bond pH, simply heating. What happens on heating? Methyl and methyl will be eliminated as ethyl, Me plus this triple bond will be coordinated here. PT, PPH3 twice, triple bond, pH. So that will be your product. Okay, then another previous year question in CSIR NET exam. Please write that question. Another previous year question. Write the question. N ligands are there, metal, here hydrogen, here an anionic ligand A. Hydrogen and A are anionic ligands. Heating in presence of a DMSO type solvent. Your question, first one, option A equal to, or first one A equal to CH2 CH3. CH2 CH3. Option 2 A equal to CH2 CF3. CH2 CF3. Option 3 A equal to CH2 OR. CH2 OR. Fourth one A equal to CH2 NO2. CH2 NO2. Okay. So order of rate of elimination. Order of rate of elimination. That is my question. Order of rate of elimination. A and H are anionic ligand. When you are A, mostly CH elimination is favored. When A is equal to CH2 CH3, CH2 CF3, CH2 OR, CH2 NO2, which case the rate of elimination will be faster. You know, most electron rich, that is the hint. Most electron rich alkyl group, high rate. Most comparing the electron richness of this marked carbon. Compare the electron richness of this marked carbon. This methyl group having plus I effect, so it donates electron density. CF3 having minus I effect, it withdraws electron density. OR also having minus I effect, NO2 also having minus I effect. So definitely order of rate of elimination 1 greater than, because first one having the highest rate, because this methyl group having plus I effect. So definitely what happens, the electron richness of this carbon is very high, so that will be eliminated along with the hydrogen. Then comparing these, all are withdrawing group. The withdrawing nature of NO2 is the most highest, NO2 greater than CF3 greater than OR. This is the order of electron withdrawing nature of NO2, OR and CF3 that we will discuss in the general organic chemistry section, GOC, in GOC. Okay, so NO2 having the highest electron withdrawing nature, then CF3, then OR. So comparing these, which one will be comparatively electron rich? Comparatively electron rich OR. So 1 greater than, 3 greater than, 2 greater than, 4. I think this will be the right answer. 1, 3, 2, 4. Absolutely, that is the right answer. Next question. It is an exceptional case. Please note this exceptional case. It is an exceptional case. Please listen. PT, Me, methyl group, iodine, and here DPP, diphenyl phosphinoethane. Okay, heating in the presence of a DMSO type solvent. Okay, please listen. Here methyl group -1, methyl group -1, methyl group -1, iodine -1. So platinum in the +4 oxidation state. Platinum in the +4 oxidation state is an exceptional case. Platinum in the +4 oxidation state is actually an exceptional case. So you have to note this exception and give a star mark. What is an exception? Normally, you know, when more than one anionic ligands are present, order of elimination CH, HH, CC, then only CX. But here concerted, not concerted elimination, here stepwise elimination takes place. In platinum +4 oxidation state, the stepwise or SN2 elimination takes place. Stepwise or SN2 elimination takes place. That means trans elimination. So CH3 and I will be eliminated, so that your product will be methyl iodide. Your product will be methyl iodide. Stepwise or trans elimination is forward. Clear? Trans elimination. So platinum +4 oxidation state. Here some additional points are also there. What will be the mechanism of this reaction? First step, I- will be eliminated. Your iodine is eliminated. Minus I-, so that you will get PT, Me. Here also another methyl group. Here your DPP, diphenyl phosphinoethane. DPP, PPH2, diphenyl phosphinoethane, metal with positive charge. Then in the next step, the eliminated I- will attack from the back side. That's the reaction. Eliminated I- attack from the back side, so that you will get the CH3I as the product. Suppose if this I- concentration is lowered, concentration is lowered. That means if the eliminated you can trap the eliminated I-. If that eliminated I- is trapped or its concentration is lowered, the eliminated I- concentration is lowered, this SN2 attack does not take place. This I- will not attack the methyl group. I- attack will not take place. In such a case, if concentration of I- is lowered, your product will be simply the concerted mechanism product ethane. Okay, first case I minus concentration is lowered, or in presence of polar solvent also. In presence of polar solvent also, you can trap the I minus. Why? Your I minus is eliminated. I minus is eliminated. You know polar solvent undergoes solvolysis to the negatively charged ion. That will be solvated. Your I minus will be solvated by the polar solvent. As a result of solvation, it is not possible for the I minus to attack the methyl group. Clear? So if you are intentionally lowered the concentration of I minus, or if you are using a polar solvent, then your product will be the usual product CH3CH3. Otherwise your product will be methyl iodide. That is the exception. Once again I am repeating, it's a rare platinum 4+ is an exceptional case. Platinum 4+, high oxidation state with 4 anionic ligand. Usually according to our order of elimination we expect this product, but actual product is CH3I because it follows stepwise or SN2 elimination, I minus eliminated and that attack the methyl group. But if the eliminated I minus is trapped, you can trap the I minus. For example, if you are using a polar solvent, what happens? The I minus is solvated by the polar solvent, so it becomes heavily solvated, so it is not possible to attack the methyl group. In such cases the usual product will be formed. So please write it as a note. So a related question, a worked out example in organometallic by Elias and B.D. Gupta. Please listen. You can work out this question as a homework. It's a worked out example in B.D. Gupta. Most probably you can expect this question in the future CSIR net exam. So a very important question. Platinum. Okay. Here CH3 is there. CH3 is there. CH3 is there. CH3. Instead of I minus OAC, here DPP, diphenyl phosphinoethane, DPP. First case, heating in the presence of a polar solvent. Second one, heating in the presence of a non-polar solvent. Heating in the presence of polar solvent and non-polar solvent. First step in such a case, first step O minus will be eliminated. You have to do it as a homework. This question you have to do it as a homework. First step, OAC minus is eliminated. OAC minus is eliminated. OAC minus. If you are using polar solvent, what happens? This OAC minus is heavily solvated, or that OAC minus is trapped. Because this is the exceptional case, because platinum in 4+ oxidation state usually prefer stepwise mechanism. Okay, so as a result OAC minus is eliminated, but if you are using polar solvent that is trapped, so SN2 attack not possible. So usual product will be get. Otherwise non-polar solvent, then stepwise mechanism CH3OAC will be your product. Okay, so practice with the mechanism. Here product is CH3OAC, unusual product. Here usual product CH3. Polar solvent, or you can decrease the concentration of OAC minus. So that's all about when different or more than one anionic ligands are present.